Once we have a skeleton equation, then we need to balance the equation so that it satisfies the law of conservation of matter. In order to do this, we first need to take an inventory of how many of each element we have on both the reactant and the product side of the equation. Once we have this inventory and we've determined that there's a need to balance the equation, because sometimes the skeleton equation will already be balanced, but if we determine that there's an imbalance in one or more of the elements, then we need to pick an element that we're going to start with. And how we go about balancing is we examine how many we have on each side, and whichever side needs more of that element, we would use a whole number coefficient in front of that entire formula so that the total number of that particular element is equal on both sides. If you have an existing amount that is like an even odd combination, 2 on one side, 3 on the other, then you'll need to resort to using the least common multiple of those two numbers. So in the case of having 2 on one side and 3 on the other, you're aiming for 6 atoms of that element on both sides of the equation, and you would use the respective coefficients in front of the formulas that would give you that total number of 6. And so you balance one element at a time. Once the first element is balanced, whatever coefficient you used not only applies to that element, but it also applies to the remaining elements or ion formulas that are in that compound. And so then the natural progression would be to then balance the next element that was affected by that coefficient that needs to be balanced. And in this manner, balancing will actually walk you through the entire equation such that by the time you get to the last element that needs balanced, it's already balanced itself in the majority of cases. Now, when it comes to selecting which element should we start with, really it doesn't matter. However, there can be some equations which will be much easier to solve and balance if you do start with a particular element, and there are some hints for deciding what ones to start with, or rather which ones to end with, to leave until the very end in the hopes that they'll balance themselves, and some ways that we can handle some of our other types of compounds. First of all, when you look at the skeleton equation, if you see that there's an element that is appearing in a lot of different locations, it's in more than one formula, or it's by itself, those elements are typically ones that are best left to balance at the very end. And mainly the reason for that is, if it's in more than one formula, then more than one coefficient is going to affect your bottom line, your total. And that can get a little tricky when you're dealing with multiple sources of the same element. The other reason is, if it's by itself, if you leave it for the end, it's kind of like sweeping up the pieces. Okay? If you get everything balanced except that one element, then whatever coefficient you stick in front of the formula of the element by itself, it only affects that element, and you're able to finish out the balancing nicely and neatly. Another hint is, if you see a polyatomic ion in one of your formulas, if that polyatomic ion is found on both sides of the equation, and it's the only source of the elements that make up those polyatomic ions. For instance, sulfate. If you have SO4 on the reactant side and SO4 on the product side, and there's no other source of sulfur that you need, then you can go ahead and treat that polyatomic ion as if it's a single unit and balance it not as sulfurs separately from oxygens, but as the sulfate ion, SO4, as a single unit. Another hint, it's not on your slide here, but when you have water, sometimes it might be advantageous to represent water not as H2O, but as HOH. And in doing so, you then have access to a hydroxide ion, an OH ion, so that if you have hydroxide on the other side of the equation, you could then treat it as a polyatomic ion and balance it separately, a hydroxide ion and a free hydrogen. Things to keep in mind, again, the subscripts in the formulas. Once we have taken oxidation numbers and written correctly written formulas, those subscripts should not be touched. The only thing that we change when we're balancing an equation are the coefficients, the multiples of how many of that formula unit we have. If we change the subscripts, we're changing the fundamental identity of what the compound is, and that's not what balancing is all about. It's not changing what we're working with, it's changing the relative ratios, or the amounts of the substances that are interacting with one another. So if we go back to our skeleton equation, we wrote the skeleton equation from this narrative, and we determined the states, we determined that copper would be a precipitate. But if you recall, chlorine is out of balance. We have 2 chlorines on the left, 3 on the right. So whenever we have this even-odd combination, obviously we're going to need more chlorines on the left-hand side currently as it stands, but there's no whole number that we can put in front of CuCl2 that's going to give us 3 chlorines. We don't want to deal with decimal or fraction coefficients, only whole numbers. So with 2 and 3, we think least common multiple is 6. So we want to use coefficients that are going to give us a total of 6 chlorines. So with the aluminum chloride on the product side, we've currently got 3, so that needs a coefficient of 2. That will give us 6 chlorines. On the copper 2 chloride side, the reactant side, we're going to need a 3 as a coefficient. Now at this point, we need to balance both the coppers and the aluminums. And so in front of the copper, we need a 3. And in front of the aluminum, we would need a 2. And now if we double check our inventory, 2 aluminums on the left, 2 on the right. 3 coppers on the left side of the equation, 3 coppers on the right side of the equation. 3 times 2, 6 chlorines on the left, and 2 times 3 is 6 chlorines on the right. Every element is balanced, and we now have our balanced equation.